Welcome to Chapter 17, Section 3. We're going to be doing Part B now, talking about Ohm's Law. So what we're going to do is distinguish between ohmic and non-ohmic materials and learn what factors affect resistance. So for most materials, resistance is constant, meaning it doesn't change, okay? And also, if we change the potential difference, the current changes proportionally. That means if we have a graph of voltage versus current here, right, as we increase the voltage, the current will increase at the same rate because our resistance is constant. So this idea, when this is true for a material, this is called Ohm's Law. So Ohm's Law is true for most materials, but not all of them. So materials that do follow Ohm's Law are said to be ohmic. And materials that don't then, okay, so if they don't follow Ohm's Law, they are non-ohmic. So you can tell if a material is ohmic or not by doing an experiment and graphing the current versus potential difference, okay? So if the graph is a straight line like the one we just showed, where this is V and this is I, okay, then this one would be ohmic. Whoops, let's see if I can spell here. Okay, but if when you graph V versus I, you end up with this curved graph like this one, okay, that means that the potential difference is not changing equally with the current, okay? So here, changing the potential has very little effect. Here, it ends up having a lot of effect. Okay, so this would be a non-ohmic material. So you can tell by their graph. So light bulbs are a great common example of non-ohmic circuit component. Okay, circuit component means it just needs to be in a circuit in order to run. So the current changes are not proportional as you change the voltage across a light bulb. Okay, and so the resistance of a light bulb is not constant. So here I chose two spots, and if we were to calculate the voltage over the current, they would have different ratios from here to here. Okay, so if we calculated them out here, it turns out that this R, R1, would be much smaller than this R, R2. Okay. Okay, as long as it curves that way, that will always be true because of how much the voltage is changing along with the current at these different points. So what things can affect our resistance and cause it to change? And when I say this, what affects resistance, this would affect both ohmic and non-ohmic materials. Okay, so what causes them to change? Why can we have different resistor values? So the resistance is affected by several things, including the length of the material, its cross-sectional area, what it's made of, and the temperature. Okay, so, just how much wire you're putting it through is a good thing about length. Cross-sectional area would be how thick our wire is. Okay, whether it is really easily to conduct material or one that's harder to conduct. Okay, is it more of an insulator than a conductor? Okay, and also the temperature. You could have the exact same wire, but the resistance will change depending on what temperature you use. So if you guys want to look more at this table, it is in your textbook. So why do we use resistors? What role do they have? Okay, well, resistors are most commonly used to control the current in a conductor because we know that a different resistance will supply a different current depending on the voltage. Okay, so they are used everywhere in electronic devices for this purpose specifically. Okay, so let's just pause here a moment, and this is a good practice problem, but it's also good to think about as we start using circuits, okay? So salt water and sweat lower the body's resistance to current, okay? So if you are completely dry, your skin has a resistance of about 500,000 ohms. But sweaty, salty skin can have resistances as low as 100. Okay, so this greatly affects what happens if you come in contact with a potential difference, right? A voltage. Okay, so the example we're going to look at is if you come in contact with 5,000 volts, okay, which is easily possible with the power lines that enter your home. Okay, what currents, right, might we find? Okay, so look at that. So I set it up here, and now we need to remember from the last one that our equation that we use is resistance equals the potential difference divided by the current. Okay, so solving that for I, end up with I equals the voltage divided by the resistance. So now we can plug it in for both our equations. So for both of them, we've got voltage as 5,000. So I'm going to have my current is equal to 5,000 volts divided by, in this first case, this is our dry skin of 500,000 ohms. When I solve that, I end up with current being equal to 0.01 milliamps, okay, or excuse me, amps, which is 10 milliamps. Okay. Now if we do the other one, this is when you're sweaty. Let's see what happens. Okay, so again, I've got I equals V over R, so I'm going to have 5,000 volts divided by 100 ohms. Okay, and as you can imagine, we're obviously going to get a much bigger number, and in fact, we get 50 amps. Okay, so these two numbers are considerably different. And it turns out that for humans, okay, 10 milliamps is painful. Okay, but anything from 100 milliamps and above, that can be deadly. Okay, so we start to feel it below 10 milliamps, but at 10 milliamps, it starts to really hurt. So if your skin was super, super dry, and please do not try this, okay, because there's a lot of other factors, okay. But in general, if your skin was really dry and you came across 5,000 volts, most likely it would just hurt a lot, okay. It would be painful. However, if you were salty at all or there were any other factors that decreased your resistance to current, okay, then you could potentially die. So this is one reason we want to be very careful, okay? The voltages we're working with in class are much, much, much lower than 5,000 volts, but it's still important to always keep safety in mind. So if you guys have any questions, this is the end of section 3, and I will see you in class.